Now, I said it in words, but let us define explicitly what is a collinear carbon dioxide molecule. In the classical description, there's a carbon with mass little m. There are two oxygens with masses capital M. They're connected by harmonic or string potentials with stiffness K. At first instant in time, one oxygen is at position x1, the other one is at position x2, the third one is at position x3. So this defines the energy of the system because it tells it what the masses are and how stretched the two springs are. And now Newton's second law says that acceleration of particle 1, 2, 3 is proportional to the force it experiences, which is the stiffness of the spring, the mass of this particle, and the stretching of the spring corresponding to particle 2. The guy in the middle has its little mass k, and it interacts with the particle on the left by stretching, and the particle on the right by stretching, and the right particle oxygen interacts with carbon by stretching. So that's our system. We can write this in matrix form because it's a linear equation on the forces. We will look at a very special set of solutions for which the time dependence factors out. So let's look at solutions which are called normal modes of the system. We'll be looking for a frequency omega such that we can separate position x at time t into a variable x1, 2, 3, and the time dependence is in this oscillatory function. If we put this in acceleration, we will have to take two derivatives, bringing it down twice, and we get an equation which is just equation for the x's, time-independent equation, in which the matrix of interactions, which these stiffness renormalized by the mass, so the natural frequencies, if you wish, for harmonic oscillators, what's acting on the first guy, what's acting on the second guy, the carbon in the middle, what's acting on the third guy, that should be proportional to omega squared to itself. And the secular determinant of this equation, h minus omega squared, its zero will give me the eigen frequencies of such a system. Now, this is 3 by 3 equation, so when I compute this determinant, I will get a cubic equation. You could stick this into Mathematical or some other algebraic program, but not in this course. Here, we have to think first before we compute. What I want you to do, whenever you approach a problem, the first thing you always ask yourself, does this problem have a symmetry?